This presentation is going to be a little bit different in the sense that I'm going to be talking about the effect of cracks in service life predictions. I think this is a topic that is very near to me because it's been the focus of my research for a long time. But I know that there's different ways to account for them, and everyone can do it in a different manner. So what I'm going to show now is by no means you should do it this way. So just keep that in mind. So every summer, the scariest movie that I see, and pretty much every summer, is the Attack of the Cracks. They always show up in projects that I work on. Sometimes I get calls from people who are working on a project and they get cracks, and the owner says, well, what about my service life now? What is going to happen to my very dear and precious structure? Is it going to cost me, do I have to replace it? Can I keep using it? What's going to happen? And in some cases, there are ways to save the structure. Sometimes there isn't. So this is I'm old enough where you could change channels until you find, you come up with a movie that is really bad, but you really like it and keep watching it. The sequel is scarier is when the cracks come back. And you've already did a repair, but something was not addressed, and then you get another call there down the road, or from another project where they tried something, it didn't work, and now what? By the way, we probably spent too much energy doing these two AI posters, but I'm going to be talking now about how do we deal with cracks? Cracks are interesting because we try to avoid them, but we know they're going to happen. All specifications that we use have a section dealing about cracks. Yet when they occur, everyone's eyebrows goes like this, and is like, okay, what are we doing? What's happening? What's going on? So even though we anticipate and cannot guarantee that crack-free concrete is going to be used, they always become scary. And understanding how cracks affect concrete, specifically into service life prediction, is a tricky thing because there is a lot of variables that can affect the performance in different ways. So assessing the type of cracks, or sometimes it's not even crack, it could be something like this, like bug holes or defects. These type of construction features or bugs will affect the way the structures behave and how you can make predictions of their behavior or performance. Some challenges are technical and some challenges are not technical. I'll talk about those in a minute. And I'm not going to be talking about repair procedures or materials, but I have two case studies that I'm going to show with you. And that also comes back to when we repair these type of structures, how we deal with the durability of the repair. Is it a repair structure just as good as the initially constructed one? And if not, why? Or how we can make these two connect each other. Part of the problem with cracks, at least in the type of work that I do, which is working for contractors rather than the owners, is how is this impacting my schedule? This is a big liability for a contractor if they cannot complete the project in time. Sometimes it's not the contractor's fault that there's a crack. Maybe there was something else going on, or let's say poor design that is unreinforced, etc. So there are a lot of stakeholders in most projects, and sometimes what happens is out of their control. Sometimes it's definitely under their control and they just screwed up, like in this slab on grade where the joints were sewn a little bit too late, and you have a beautiful crack that goes perpendicular to almost every panel. And now the owner is rightfully concerned that their structure that they spend money on is not going to be performing the way they want. And sometimes that is correct, and there's a need for addressing the situation in perhaps a different way. And each project is different, so every type of crack manifests in different ways, and the way to assess them and prepare for them is different. Sometimes the issue becomes who's accountable for the situation and how to remediate it is perhaps some of my most typical type of project discussion when I get involved in projects. These are just some photos of projects that I've done. Some of the technical challenges that I mentioned is how do we deal with contract documents dealing with cracks? Some of them, like I hope this section like here, I hope it can be read by everyone, but it talks about cracks, and then this sentence right here, the resulting crack repair shall be watertight. What does that mean? Anyone knows what watertight means? I mean, it's an easy concept to grasp, but what does it mean? How do you prove that something is watertight? Sometimes they specify a very restrictive form of repair material. And I already mentioned why we do this, because we don't want to have the cracks affect the structure, but in reality is that specifications can really cover all scenarios. Having flexibility in the way we address them is critical to make sure that the performance of the structure is what we all want in the end. And sometimes there are not technical challenges. Sometimes there's not much time to fix the cracks, and maybe alternative solutions have to be derived. Sometimes the cost of repairing the cracks is substantial, and then you're going to a situation where you're probably telling the contractor, you better punt this one, rip it out and start from scratch. And sometimes it's just communication. There's an adversarial relationship between the owner and the contractor, or the engineer of record and the contractor, and they don't agree on how to do things, and the schedule keeps being eaten by. So sometimes they just say, well, rip it out and start again, even though it was concrete that could be saved. I'm going to show some slides because I wanted to emphasize the effect of cracks, and Marwa had one in her presentation that looks very much like this. A lot of people say, well, when you have a crack in your concrete, all the chlorides reach your rebar immediately, and that I don't believe that. These are graphs showing that depending on the surface crack width at the surface, the ingress of the chlorides will be increased for wider cracks, and that's similar to the profile that Marwa showed of a crack specimen. You don't see a flat line up to the entire depth of the concrete cover, and then supposedly where it's on crack, it starts diffusing. It just always looks like this. So if it looks like this, it means we can predict this behavior in some way, because it just means that depending on your crack width, your transport is going to be increasing for specific conditions. And the other thing that also is important to note is that even material differences have an effect on this. So the cracks, even though they're important, is not the only parameter that is playing a role in this type of predictions. These are some photos of analyses that were made on crack specimens, and we inspect them with laser ablation equipment to understand how chlorides transport not only within the cracks but into the concrete, because you cannot determine the chloride content in a crack, right? It's a void, it's a cavity. You cannot extract that and then measure it. Maybe the pore solution there is something you could extract and use, but in practical terms, it becomes really complicated. And again, here, you can see that for Portland cement, you have a lot of distribution of chloride contents for various crack widths. When you work with other materials, like this is CM3B concrete, that there's an attenuation on the chloride concentration for the same concrete geometry, the same concrete mixture in general with two different cements. So again, the material that you're working with in a crack, on crack condition, has an effect on how make the prediction. So this is a conceptual model that I worked on a long time ago that I still use. Is when you have a crack, depending on the crack features, you're basically reducing. You can approach it in two ways. You can assume a reduced concrete cover thickness. So say you have a narrow crack means I have slightly less cover in that location. Or you can assume an increase in your transfer properties in this way. Again, some people may use it differently, but this is the one that I use because it's simple and it can be adjusted for project-specific conditions. For example, this parameter here is the on-crack diffusion coefficient. This is the crack width on the surface, and this is the crack width limit. And this is perhaps the one that it requires a little bit more explanation. There's a point where when you have a large crack, your transport properties start to be such where you can assume that there is almost no concrete cover. And that is a difficult value to determine in most cases because it's depending on exposure conditions, the type of crack, etc. But for the most part, it's going to be in the order of maybe 400 microns to 500 microns for the projects that have been involved where we have cracking problems. And one of them is, since we're in Canada, I brought a Canadian project. This is a bridge in Manitoba that was constructed in 2012, and even before commissioning, there was cracking on the concrete deck. And the specification was very good. They met all the strength requirements, all the chloride penetration, RCPs of less than 1,000 coulombs. Everything looked great except for shrinkage. No one thought about shrinkage, and then probably you cannot see them here, but you can see some of the cracking. This is a crack map of the project. And then obviously the Ministry of Transportation is concerned about how much does this crack affect my service life and what can we do to save the structure. In this particular case, crack repair and overlay was the best solution. And we all came back to the most used and abused table of all ACI, which I think is this one. What are reasonable crack widths? And the term, the definition of reasonable even has an asterisk here. It's like, well, what the hell does that mean? And it all depends on the judgment on the engineer who's doing the analysis. For some of us, these values can be slightly not conservative enough, and for others, they could be conservative enough where they can make predictions based on these parameters in their analysis and their modeling. But for probably 8 times out of 10, these are going to be a good indication of where you should start looking at crack repair or other methods to address cracking. This is just a prediction on the service life of this particular bridge. Even though there was no service life requirement, when the owner asks, how much am I losing, you have to start from scratch and make a prediction. So for this bridge, if everything had gone well, they were probably going to be getting something in the range of 50 to 60 years. So we have a predicted chloride ingress, reliability index, so they match together. So that's what they were most likely going to get if someone had paid attention to shrinkage. But because they didn't, now they have lost about 30 years of service life. And that is the point where you start discussing, okay, this is not acceptable for us, or we cannot permit to start having problems with my bridge in 20-some years. What can we do? And then we talk about crack repair, an overlay, etc. So this is an example of how we can save a structure that has problems without having to rip everything out, and ultimately, like in the example Marwa showed, alternative repair methods are sometimes sufficient to make sure that we can keep working or the project can continue. And the second study that I'm going to show is some weir slabs, weir slab and weir walls that had some cracking. I'm going to focus on the slab because it's perhaps the most critical structure, and you can see that these cracks are huge. I guess something I forgot to mention is when you deal with relatively narrow cracks, what I found is that they have a different distribution, typically a log normal or beta distribution, depending on the information that you get, and if you do a goodness of fit analysis. I tend to see that smaller cracks are going to be mostly concentrated around the average. When you start looking at large cracks like this, distribution widens up, and then you start in the normal distribution range, and you can account for for those type of distributions in your modeling if you're using probabilistic analysis. But in this particular case, see, again, no one paid attention about service life until the cracks appeared, and this structure was probably not good, a very good one to begin with. They were probably going to be getting somewhere in the less than 30 years before they had to start doing, spending money on fixing things. And with the cracks that they had, well, it was a really big problem. So in this particular case, the decision was, okay, we cannot keep this, let's rip it out, start from scratch. So every project is different. I'm not saying that it could not, this lab could not have been saved somehow, but again, time constraints, the contractor doesn't want to delay the project. They would just want to say, well, we screwed up, let's do something different, and they kept going with the project. I don't have much else to say. I'm just going to probably leave it now for questions, but this is the way I approach cracking in service life predictions. I hope it was useful, and thank you for your time.